So then let's start. So basically today's topic is azeotropic mixture. Azeotropic mixture. See, what is azeotropic mixture? Samya, am I audible to you?
Yes, sir.
Okay. So today's topic starts from here, azeotropic mixture. See, what is azeotropic mixture? So I'm going to define it. Any solution which is binary. For azeotropic mixture, it should be binary solution. You know what is binary solution? A solution which contains only two components. Only two components. So the first condition for being azeotropic mixture is it should be binary solution and a fixed composition. A fixed composition. It shouldn't be like that. It shouldn't be like that. You are going to mix the two component in any proportion. It should be in fixed composition. And the third is basically constant boiling point. After mixing fixed composition of a binary solution, their boiling point is constant. So constant boiling point due to which fractional distillation is not possible. Due to which fractional distillation is not possible. Do you know what is fractional distillation?
No,
Anyone?
sir.
Okay. So I'm going to tell you what is fractional distillation. See, if in a beaker we have a solution, in a beaker we have a solution, that means there is two component. That means there is two component. It's like this. In this, A and B is present, A plus B. Since these are two components, different components, these two components will have different boiling point. Yes or no?
Yes.
Yes.
If just suppose A has a boiling point of 100 degrees centigrade and B has a boiling point of has a boiling point of 60 degrees centigrade. So fractional distillation is a method to separate components from each other. So you are going to heat it at 60 degrees centigrade. And what happens at 60 degrees centigrade? B will evaporate and it will, here it is closed, and B will evaporate and it will be in gaseous state and it will travel it from here to there. And here it's, you are going to do it, you are going to cool it. Their cooling process is here. So B will, all the B components will evaporate and go to this section, and if you cool it, it will be again in liquid form, and A will be left pure. So this is basically extraction of from this mixture. Okay, this method is called fractional distillation. Is that clear, both of you?
Yes, sir.
So basically what happens here, actual here is also two components, but in azeotropic mixture, when they mix in a fixed composition, their boiling point becomes same or equal. So it is impossible to do fractional distillation after mixing it in a fixed composition. And when it becomes azeotropic mixture, that means A and B will have same boiling point. So it is not possible to extract B from A or A from B. Are you getting my point, Reem and Samia?
Yes, sir.
Yes, sir.
So this is basically fractional distillation. So what is azeotropic mixture? Azeotropic mixture is a binary solution which mixed in a fixed composition, and after mixing, their boiling points become same. That's why it is not possible to do fractional distillation. Just like if you have C2H5OH plus H2O, if you are going to mix ethanol into water, and if ethanol is 90% weight by weight, then it will be a azeotropic mixture. If you are going to change the composition, then it won't be azeotropic mixture. Are you getting my point? Reem, Samia?
So can you repeat once?
Yes. What I am telling you is C2H5 ethanol plus water is an azeotropic mixture when ethanol is 95% weight by weight. This is fixed composition. If you are going to change the composition should be fixed for azeotropic mixture. If you will change the composition, it won't form azeotropic mixture. Okay. So for an azeotropic mixture, the composition should be fixed. Got it, Rim and Samia?
Yes, sir.
Yes, sir.
Okay. Please write it and let me know when you are finished. Today we are going to finish this chapter. After this topic, we are going to take Vant'hoff factor and do practice on Vant'hoff factor. And after this chapter, we are going to start electrochemistry.
Sir,
Yes, Samia.
can you please once explain positive and negative deviation?
Yes, why not? Just write it and then I will explain it to you.
Okay.
Okay. Anything else from the previous lectures or any concept that you haven't understand till in this solution chapter, because this chapter is going to end in this lecture. So if
Yes,
you
sir.
have any
Non-ideal.
okay, only non-ideal solution with positive, basically only non-ideal solution. Okay, I will explain it right now. Just write it and then I am going to explain it.
Done, sir.
Done. Very good, Rim. Samia, let me know when you are finished.
Done, sir.
Very good. So I'm going to explain non-ideal solution. And for non-ideal solution, you need to see ideal solution also. So see, what happens here is, you can see ideal solution is one which follows Raoult's law. That means observed total pressure is equal to calculated total pressure. Delta V mix is equal to 0. Delta H mix is equal to 0. And also delta G less than 0. Delta S greater than 0. And also the fifth condition, which is very, very important. This interaction part is very important. Why it's it is, wait a minute. It was erasing by itself. I was writing and it was erasing. Oh, see this. Okay. Is the screen visible to everyone?
Yes, sir.
Okay. See.
Yes, sir.
This interaction part is very important. A is pure, that means another container, and B is pure, another container. The interaction between AA particle and the interaction between BB particle should be equal to the interaction between the solution particle. And in solution, we know that A and B particle both are present. This is ideal solution. What is non-ideal solution? Opposite of ideal solution is non-ideal solution. So for non-ideal solution, a solution which do not follow Raoult's law is non-ideal solution. Apart from this, delta V mix not equals to 0, delta H mix not equals to 0, delta G, this is constant, and this is not equals to this. So what should be what is the value of basically delta V mix? In case of ideal solution, it was delta V mix is equal to 0. But in non-ideal solution, you can see it is not equal to 0. It is not equals to 0. It is not equal, total pressure is calculated pressure is not equals to observed pressure. And the interaction between AA particle and BB particle is not equal to the interaction between solution particle. So it is what is basically non-ideal solution? So basically non-ideal solution has two parts. A solution which shows positive deviation with non-ideal solution, non-ideal solution with positive deviation, and non-ideal solution with negative deviation. See, in non-ideal solution, you can see PT greater than PA plus PB. That means observed pressure greater than calculated pressure. Are you getting my point? Observed pressure greater than calculated pressure. And if pressure is greater, that means we are talking about basically vapor pressure. Now see here, this is very important part. It shows that pure particle of A and pure particle of B has more force of attraction than the solution particles. That means it has more force of attraction. That means AA and BB, which is in pure state, will have lesser vapor pressure or not? Which has lesser vapor pressure or not? If force of attraction is greater, that means vapor pressure is lower or lesser?
Yes.
Yes. And you can see solutions particle will have lesser force of attraction. That means it will have more vapor pressure. That's why when we draw the graph, the straight line is basically for ideal solution. And with respect to ideal solution, if you go for positive deviation, that means will have the solution particles will have less force of attraction. That means it will have more vapor pressure. That's why total vapor pressure is like this. Are you getting my point?
Yes.
Again, if you go for non-ideal solution with negative deviation, you can see PT less than, observed less than, calculated, delta V mix less than, and you can see the solutions particle has more force of interaction than pure particle. That means solution particles will have more force of attraction. That means vapor pressure is lower, decreases, yes or no?
Yes.
And if vapor pressure decreases, that means the straight line is for ideal solution. The graph will be like in the lower form, because it has lesser vapor pressure. That's why you can see the total vapor pressure is lesser. This is the difference between positive deviation and negative deviation. Samia,
Yes, sir. Clear.
is this clear now?
Yes, sir.
Okay. And in azeotropic mixture, we are going to do the same. Are you done with this?
Yes, sir. Yes, sir.
Now see, azeotropic mixture forms two types. Azeotrops. These are of two types. See, minimum boiling point. Azeotropic mixture with minimum boiling point. And here, maximum boiling point. And it is of basically non-ideal solution. Non-ideal solution. I am going to ask a question. Which one will have minimum boiling point, positive deviation or negative deviation? This is my question. Which one will have minimum boiling point, positive deviation or negative deviation?
Negative.
Negative.
Positive.
See, rim positive deviation has more vapor pressure or less vapor pressure. Rim positive deviation has more vapor pressure or less vapor pressure. Rim, you are not audible.
So it's more.
More vapor pressure. If more vapor pressure creating, that means lesser boiling point. If vapor pressure is more, that means force of attraction lesser. That means boiling point is less. Yes or no?
Yes, sir.
So whenever minimum boiling point, when I say minimum boiling point, that means positive deviation. That means positive deviation, because in positive deviation you saw that vapor pressure is more. That's why minimum boiling point. And maximum boiling point will shown by negative deviation. Negative deviation. Please write it. Negative deviation. Now you can see C2H5OH. This is mole fraction of C2H5OH. And since, wait a minute, why it's saying that? Mole fraction 1 because it is pure here, and mole fraction of H2 on the right hand side is 1, but positive deviation, so the graph will be like this. If vapor pressure is more, that means that means boiling point is lesser. That means boiling point, you can see the boiling point will be lesser. It will be like this. No, wait. This is the graph for positive deviation, and if you are going to draw for negative deviation, it will be like this. This is shown by negative deviation shown by HNO3 with water, mole fraction of H2O. Sometimes it hangs. 1, 1. If the graph is like this, for negative deviation, you can see it will be like this. Please write this. Always remember, this is a fixed composition is fixed. So when HNO3, wait a minute, I'm going to cut it down. For azeotropic mixture, the composition should be fixed. So HNO3 plus H2O, and the composition should be HNO3 68% weight by weight. Like if you are going for C2H5OH, as I already wrote it. In this, composition should be 95% weight by. Okay, please write it. Madhya, you didn't solve the test.
Sir, I did.
But you didn't send the test, right? In the group.
I sent the test also in the group.
In the group you sent the test. I only got from Samia and Rim. In which group you have sent? What is the name
The
of
one that they created with G.
no. What is the name of the group? Do you know?
Yes, sir.
Tell me.
It is Hassan Raza's chemistry, and then in the brackets written G for girls.
Hassan Razani. Hassan sir, chemistry G is I'm added in this group, and I think Samia is also there. And Rim, are you in this group?
Yes, sir, I'm there.
Okay. Please check it out. Please write it. Let me know when you are finished with this.
Done, sir.
Done, sir.
Okay. Now the second topic comes Vant'hoff factor. And Vant'hoff factor is denoted by I. Before starting Vant'hoff factor, we are going to see what is abnormal molar mass. So I'm going to define it first, then I will explain it. Write with me. Abnormal molar mass. So when non-volatile solute, solute is added to volatile solvent, that is understood, volatile solvent, and it undergoes association or dissociation. Undergoes association or dissociation. Then the molar mass, why it is hanging so much? Wait a minute, please. Is my voice lagging?
No, sir.
Kind of, sir.
Okay, thank you. Then the molar mass of non-volatile solute is calculated from colligative property will be different from its normal molar mass. Normal molar mass. This is known as this is known as abnormal molar mass. Abnormal molar mass. So please write it first, then let me know, then I will explain. Let me know when you are done with this.
Done, sir.
Done. Very good. Everyone done with this? See, what is abnormal molar mass? When you are going to add a non-volatile solute, then the solute can be associated or dissociated. It depends upon the nature of solute. And if you are going to calculate the mass with the colligative properties calculated by colligative property, it will have different molar mass. It will have different value than normal molar mass. That is called abnormal molar mass. I am going to give an example. Just suppose you are going to take NaCl. Oh, wait a minute, why it's not working? Sorry. Now see, if you are going to add NaCl in a volatile solvent, NaCl will be dissociated into two ions, cation Na plus and Cl minus. Can you tell me the molar mass of NaCl? Please let me know the molar mass of NaCl. Anyone? Am I audible?
So 56.
56. It's wrong.
45.5.
58.5 gram. See, before, see, here is a container in which NaCl is present. Here is another container in which H2O is present. And if you are going to mix it, then the solution will be like Na plus Cl minus and like this. And you can see, if you are going to pick 1 mole from here, 1 mole, that means it will be equal to its molar mass 58.5 gram. Yes or no?
Yes, sir.
If you are going to pick 1 mole from this container, it will have a value 58.5 gram. Initially it was pure, then it was in this form NaCl, but when you put this in water, it will be in Na plus and Cl minus, and Na plus will have 1 mole of mass 23 gram, and Cl minus will have 1 mole of mass 35.5 gram. Yes or no? Yes or no?
Yes.
And after adding NaCl into water, if you are going to take 1 mole of anything, either Na plus or Cl minus, it will have, if you are going to take Na plus, it will have 23 gram, and if you are going to take Cl minus, it will have 35.5 gram. So before mixing into solid, before becoming solution, it has 58.5 gram molar mass, but after dissociation, you will get either 23 gram and 35 gram, 35.5 gram. This is abnormal molar mass. This is normal molar mass. This is abnormal molar mass. Are you getting my point? And this is for dissociation. This example was for dissociation.
So which one is abnormal?
This one. You will see that. Okay.
Okay.
Now see, this is an example of dissociation. I am going to take an example of association. CH3 COOH. Can you tell me the molar mass of CH3 COOH? Anyone? Please calculate molar mass of CH3 COOH. Can you calculate molar mass of CH3 COOH?
60.
60 gram. When you are going to put this CH3 COOH in a solvent, then there will be a hydrogen bonding between 2 moles of CH3 COOH, and it will be like this. Basically, this compound dimerize. This compound will dimerize. Oh, wait a minute. I did wrong. CH3 C double bond O OH, and here it will be double bond O, and again here it will be OH, and again CH3C. So basically 2 moles of CH3 COOH, that means ethanoic acid, dimerize to form 1 mole. This is dimer. Initially it is 60 gram, and since this is 2 mole, and after association it forms dimer, what will be the molar mass of this? Can you tell me? 60 gram for 1 mole, and it joined together 2 moles. 2 moles form 1 moles, then it will be 120 gram or not?
Yes, sir.
So basically you can see molar mass changes. This is basically this is called abnormal molar mass. Are you getting my point? This is normal molar mass. This is abnormal molar mass.
Yes, sir.
And this arises due to this association or dissociation. Please write this example. There will be more formula for Vant'hoff factor. Please let me know when you are done with this.
Done, sir.
Done, everyone?
Done, sir.
Madhya?
Done, sir.
Thank you. Now see, I'm going to define Vant'hoff factor. Vant'hoff factor I. So basically, I'm going to define it. Please write with me. It is defined as a ratio of number of solute particles. Ratio of number of solute particles before association or dissociation. Before association or dissociation, and number of solute particles wait a minute. Before, not after association or dissociation. 2, number of solute particles before association or dissociation. So this is it. Formula for I. I will be equal to number of solute particles, after dissociation or association, upon number of solute particles before dissociation or association. I will give some example, you will get it. Please write this. I has a formula, number of solute particles after dissociation or association upon number of solute particles before dissociation or association. Are you done with this? Please let me know when you are done with this.
Done, sir.
Done, everyone?
Done, sir.
Very good. So see, I'm going to take an example, NaCl. So NaCl will be dissociated into two parts, Na plus plus Cl minus. Now initially it is 1 and 0, 0. But after dissociation, it will be 0, it will be 1 and 1. So I will be equal to, since it is dissociation, count the number of moles of solute particle, count the number of solute particles After dissociation, 1 plus 1, this will be equal to 2 after dissociation upon initial before dissociation, it will be equal to 2 by 1. That means I is equal to 2. That means I is equal to 2. Everyone got it? Rim, Samia, and Madiha. Rim, are you done with this?
Yes, sir. Sir,
Very
one,
good.
sir, one.
Okay, take your time. Just let me know whenever you are finished.
Yes, sir.
Very good. Thank you. Now see, I'm going to give some question. You need to write the equation, then find the value of I. Calculate I for all the reaction, all these two reactions. And the fourth I'm going to give you. I'm going to write this equation in the last reaction. Please do this. Done.
Sir, can you explain?
Yes. See, it's very easy. If you are going to dissociate it, it will be Mg plus 2 Cl minus. Yes or no? Samia,
Okay.
this will be the balanced equation for this. Yes or no?
Yes, sir.
Now I is equal to, after dissociation, it converted into, you have to make it balance. After dissociation, it is becoming 1 plus 2, that is equal to 3. And before dissociation, it is only 1. So 3 by 1, that means 3. Got it or not?
Yes, sir.
Again, Al to Al plus 3, it will be changes into Al plus 3, and it will be SO4 minus 2. But you have to make it balance. So for balancing, 3 SO4, so multiplying it by 3, Al2 multiplying it by 2. Now it is balanced. Now see, after dissociation, it becomes 2 plus 3 particles, that is 5. And before dissociation, it is only 1. So I is equal to, after dissociation, 5 upon 1. That means I is equal to 5. Samia, got it, everyone?
Yes, sir.
Now see, this is basically association. These 3 examples are 1, 2, 3 is for dissociation. Now you can see 2 is becoming 1. I is equal to, after association or dissociation, since here it is associated. So 2 is 1 mole. So 1 after association it is 1, and before association it was 2. So I is equal to 1 by 2. Always remember that for dissociation, I will be greater than 1, and for association, I will be less than 1. Why? Since for dissociation, it will be always dissociated into more molecules. So in numerator, we have greater number than denominator. That's why for dissociation, I will be always greater than 1. And for association, 2 is becoming 1, 3 is becoming 1, lesser than the initial. And in numerator, it will be smaller than the denominator number. That's why it is I less than 1. Are you getting my point?
Yes, sir.
Please write it. Everyone? Madhya?
Yes, sir.
Okay. Let me know if you have any doubt.
Done, sir.
Okay, very good. Sania, you are also done with this?
Yes, sir.
Now see, I'm going to take another formula for I, Vant'hoff factor. The another formula for Vant'hoff factor, I is equal to normal molar mass, normal molar mass upon abnormal molar mass, upon abnormal molar mass. Now you can see normal molar mass and abnormal molar mass. As I told you, this is normal, and normal has a value. We have discussed, this is 60 gram and this is 120 gram. So what will be the value of Vant'hoff factor in terms of molar mass for this? Normal molar mass 60 and abnormal molar mass 120 is equal to 1 by 2. Yes or no? It is the same answer, as the answer is same with the different formula. So I can also be defined as the ratio of normal molar mass to abnormal molar mass. Okay.
Done,
Let me
sir.
know when you are finished. Maria, you are also done?
Yes, sir. Done.
Okay. Now I have a question on this. Normal molar mass of benzoic acid is 122 gram per mole, and abnormal molar mass is 244 gram per mole. Abnormal molar mass is 244 gram. Calculate I. Please do calculate. Let me know when you are finished.
Sir, is it 0.5?
Yes, it's 0.5 because you know the formula I is equal to normal molar mass, that is 122, and abnormal molar mass, that is 244. So the answer will be half. Okay.
Yes, sir.
Okay. Maria, are you done with this?
Yes, sir. Done.
Now see, we have another formula for I, Vant'hoff factor. Vant'hoff factor I is equal to observed colligative property upon calculated colligative property upon calculated colligative property. So basically observed colligative property is equal to I into calculated colligative property. Calculated colligative property. Please write this.
Done, sir.
Very good. So we are going. I'm going to modify all the colligative properties formula. You know, pi is equal to observed colligative property will be equal to I into MRT. I into MRT. This is for osmotic pressure. Another delta TV, that means elevation in boiling point. Delta TV will be equal to I into KB into M. KB into M. Then depression in freezing point. Delta TF will be equal to I into KF into M. I into KF into M. Then again, the fourth colligative relative lowering in vapor pressure will have a value P naught A minus PA upon P naught A will be equal to I into mole fraction of solute. Mole fraction of solute. Please write it and let me know.
Done, sir.
Are you done, Samia?
Done, sir.
What you just said?
Sir, 1 second.
Okay.
Done.
I'm going to give you some questions. Please try. Please do this question. These two questions are based on Vant'hoff factor. Please answer.
So the answer for the first one is 3.
Wait a minute. For the first one, your answer is
3.
3. Very good. Barium hydroxide, you know that. BaOH whole twice. So if you are going to dissociate it, it will be Ba plus 2 plus 2OH minus. So after dissociation 1 or 2, 3 moles. So I will be equal to 3 by 1, which means 3. Madhya, did you get the answer? Samia?
Yes, sir.
Yes, sir.
Very good. Please do the question number second. Can you do it or not?
No, sir.
Question number second, you can see. We need to calculate at 25 degrees centigrade, the higher osmotic pressure. Osmotic pressure has a value. Pi is equal to IMRT. You will always apply this formula. Pi is equal to MRT. You know that temperature is constant, R is constant, and it is also given that 0.1 m. That means m is also constant. All the osmotic pressure now depends upon I. See, glucose is non-volatile. That means it won't be dissociated. I is equal to 0. Urea will also be equals to 0. Here I will be equal to 3, and here I will be equal to 2. If you are going to dissociate it, you will get it. I is equal to 2 and I is equal to 3. So the one which has higher value of I will have higher osmotic pressure. So answer is C. Got it? Sami and Madhya.
Yes, sir.
Done, sir.
Very good. Now going to give you another question. Please do this. The question on Vant'hoff factor is very easy. So the question is, which of the following salts had same value of I, that means Vant'hoff factor, as that of K3, Fe, Cn whole 6. This is Cn whole 6. And I'm going to give you option as A is Na2SO4, B is AlNO3 whole thrice, AlNO3 whole thrice. Wait a minute. AlNO3 whole thrice, and then C is CaCl2, and D is NaCl. Please do this. Let me know if you are unable to solve it.
Yes, sir.
Done, sir.
Samya, do you need any explanation?
Yes, sir.
Now see, Samya, which of the following salts have the same value as K3? So if you are going to dissociate it, you will see this will be converted into 3K plus. Since K is potassium, potassium will have positive charge K plus, and since it is 3, so I just multiplied it by 3. And here it will be FeCN whole 6. Since here 3 positive charge plus 1 into 3, so it will be minus 3. Now after dissociation, you can see 3 particle and 1 particle 4 upon before it is only 1. So I is equal to 4. And now you are going to see which of the options will have 4, the value of I is 4. So if you are going to dissociate this, it will be 2Na plus SO4 minus 2. So you can see initially it is 1, but after dissociation 2 plus 1 3, it will have a value 3. Now if you are going to dissociate it, it will be converted into Al plus 3, and this will be 3NO3 minus. NO3 will have a negative charge and 3. So I is equal to after dissociation 3 plus 1 4. And if you are going to dissociate it and you will calculate, I will be 3. And if you are going to see this NaCl, I will have a value 2. So the answer is B.
Yes, sir.
Please write it. Done?
Yes, sir.
Very good. Wait a minute. I'm going to share another screen for question. Is the screen visible?
Yes, sir.
A new screen. Question number 41. Right.
Sir, is it C?
C.
Vant'hoff factor undergoes dissociation in one solvent and association in another solvent is respectively dissociation greater than 1 and it is less than 1. Very good. Question number 37, please.
Sir, is it A?
Which one of the following electrolytes has the same value as Vant'hoff factor as this? See how many, what is the value of I for Al2SO4 whole thrice? What is the value of I? 4 or 5?
Oh, sorry, 5.
5.
5?
Yes, 5.
5. So Answer will be, I think, C. Since if you are going to see, it will have a value 4, it will have also value 4, it will have value 3, and if you are going to subtract, it will be 4k plus FeCN whole 6 raised to the power minus 4. So 4 plus 1 will be 5. Is it done?
Yes, sir.
This question we have already done. Wait a minute, please. This that. Please do question number 57 and 59.
So is 57C?
Yes, 57 is C. Very good. What about 59?
So for 59, should we use I into KFM?
59 we use, yes, I into KF into M.
Sir, is it A?
Minimum freezing point, A will be answered because I has a 2 value, here 3 value, and it is not C2H5H since it is decreased. What is the value of I for this?
Eight.
8. Minimum freezing point will have a value A. This is 0.05. Wait a minute. The correct answer is A. And we use the formula same, delta TF is equal to IA into KF into M. M is given, just you have to calculate